The search for life in the solar system is all about the search for water. Wherever you find water, you find life. And so it seems natural that astronomers are going to start searching for water worlds out there across the universe. Water world exoplanet. But water can take a lot of forms. And recently, astronomers have announced the discovery of a steam world exoplanet designated GJ9827d. And this planet is absolutely not habitable. You're looking at a rocky core surrounded by an enormous atmosphere of steam. The temperature on the surface of this planet is 600 Kelvin. It's a steam world, and yet it fulfills that criteria. It is a water world of a type, and it is the beginning of what will eventually become a long line of various kinds of water worlds. My guest today is Eshan Raul. He is a PhD student in astrophysics at the University of Wisconsin-Madison, and he worked with a team from a bunch of other universities, including the University of Montreal here in Canada, and they found this world and analyzed it with both James Webb and the Hubble Space Telescope and are very sure that it is this strange steam world. So I interview Eshan Raul about this steam world, and then we also talk about a lot of other ideas. His specialty is in studying and characterizing exoplanet atmospheres. And so obviously I'm very interested in biosignatures, technosignatures. Where does this go from here? And so we talk about the analysis of GJ9827d, but also what are the other possibilities of exoplanetary atmospheres? Yes, we talk about TRAPPIST a bit. All right, enjoy the interview. Eshan, give me a sense of this planet that you and your collaborators have found.
Yeah, so the planet's name is GJ9827d, and essentially the big result of our paper is that it's the first steam world that we've ever detected to date. And this is especially exciting because I got to be one of the people on the team that explored this result and finally discovered it. So I guess one of the things that I think is very important about it is, water is, it's not too surprising that we detected water in the spectrum, because given how stupidly abundant water is in the universe. I mean, you can go and ask the people who study protoplanetary disks and the sheer amount of water they see everywhere. Using our James Webb data alone, we're already seeing heavy preferences for water in the atmosphere given our retrievals. However, the same planet was also observed with Hubble the past couple of years, which is kind of crazy to think about how it's still helping us with science today. But when we combined our data with the Hubble data, which was 10 whole transits of the planet were observed with Hubble, we were able to push our detection to the 3 sigma detection threshold. We're already certain that the only molecule that could observe the data we were seeing was water. And while there is some uncertainty in our calculations of exactly how much water makes up the atmosphere, the retrievals that we were carrying out found that the type of atmosphere that best explains the data is 100% water. And this makes it the smallest warm sub-Neptune to date where atmospheric absorbers have been detected.
Wow. Okay. Now I got about 1,000 questions to go in different directions. I'll see if I try and run them through one at a time. But so let's just talk about the physical characteristics of this planet. What do you think it is in terms of mass and radius and orbital rate and so on?
So in terms of mass and radius, I have to pull up the actual statistics, but it's a little bit bigger than 2 Earth radii. That's sort of what we've gotten from a lot of different observations that have been done on the planet. I think one of the big things that is important to highlight with observing planets like this is the radius valley in the small planet exoplanet population. I'm sure you're probably familiar with it, but essentially it's a gap in the population of small planets, let's say about 1.8 to 2 Earth radii, and planets orbiting F, G, and K type stars, the sun obviously being a G type star for reference. There's multiple theorized explanations of why the radius gap exists, be it photoevaporation or core-powered mass loss, but basically we don't really know what's going on in this type of regime. So,
is that the same that I've heard as the sub-Neptune desert? Is that the same thing?
That could refer to the same thing. I'm not sure if I've actually heard that term before.
Okay.
So despite this hole in the population distribution, there's still a handful of planets in the gap, obviously, especially around low mass stars. And these are exactly the type of planets we're looking at with our JWST program. So GJ9827d is a small sub-Neptune orbiting a K-type star, which makes it particularly interesting to us and is why we picked it as one of the planets we're observing. So I guess to give a little bit more context to the radius gap and all that, the planets below it, are what we call super Earths, which are likely rocky in composition, with a rocky and iron core, with or without atmospheres. And above the radius gap, let's say around 2 to 4 Earth radii, are the sub-Neptunes, which are particularly what we're observing with this program. And I think what's really cool about it is the Kepler space mission told us that these types of planets are actually likely the most common type in the universe, which, something I think a lot of people don't think about, given we don't have one in our own solar system.
Right. Or a super Earth.
Yeah,
really,
that too.
Yeah. Lucked out on both of those.
Yeah. So it's generally thought that most sub-Neptunes are likely low-density planets with cores made of icy or rocky material surrounded by a mostly hydrogen envelope. However, this hydrogen and partially helium envelope are especially vulnerable to atmospheric loss as you get closer and closer to the radius valley. So once you start looking at these low-density sub-Neptunes that are actually in the radius valley, the composition of the planet becomes ambiguous. It could be one of many different scenarios. It could have a metal-rich atmosphere, it could be a Hycean world, or it could even be a water world. And basically the point is mass and radius measurements alone aren't enough to figure out what kind of planet we're looking at by just looking at the density. So that's why we're doing transmission spectroscopy to, figure out how we're doing that. Right. And then
it is tricky. It is really tricky to get all that information purely from the transits alone. You're not getting any radial velocity data, right? Just the transit?
Yeah, it's just the transit. And so, I'm sure you're pretty familiar with transmission spectroscopy. I wish I had a cool animation to show here or something.
We'll put some up. Don't worry.
But, as a planet passes in front of its host star, at least from our perspective, the molecules in the atmosphere absorb some of the starlight. And the key is that the different chemicals that make up the atmosphere absorb the starlight at different wavelengths. So every wavelength we're observing at is like a different snapshot of the atmosphere of the planet, basically. And if you plot the fraction of the absorbed light or the transit depth against the wavelength, you get the transmission spectra of the planet. So the big question is, how do we tell the molecules, from the transmission spectrum? And that's where I come in doing atmospheric retrievals. So the code I'm using, which is aptly called Poseidon, just does this by running a million or so models on the spectrum and by generating different possible combinations of what molecules might make up the atmosphere, and finds a better and better fit to the spectrum based on the known wavelengths of what different molecules tend to absorb light at. It eventually narrows in on the combination that best explains the transmission spectrum.
Now you get multiple opportunities for the transit. I mean, there's not just the transit when the planet passes in front of the star. You get when it's going behind the star and then when it's appearing on the other side of the star. So were you able to get all of those versions of the transit or just the ones passing in front?
We're just focusing on the ones where it's transiting in front. Yeah.
Yeah. But you said you got, 10 transits from Hubble? And
yeah, so that was with a different program that was observed in the past couple years, and we used the Hubble data in combination with our JWST data in order to, strengthen basically our findings of, we really are finding a water world here.
Yeah. Now, I think it's important to be clear that this is not a habitable world just because we're seeing water. You say steam, that doesn't sound good. So how close to the star is this planet? Definitely inside the habitable zone?
So this planet, that is a good question. I don't know the exact semi-major axis of the planet, but the important thing is that it is on the hotter side of the sub-Neptune regime. It's at some 600 Kelvin. So when people hear terms like water world, they get super excited because they think, oh, water must mean oceans. Oceans must mean origins of life. Origins of life must mean aliens, right? And that's not what this planet means. 100% water atmosphere, which is, what we were finding with our retrievals, means exactly that. There's like no oceans, but just straight up water from the top till you reach the core. So that's at least with our understanding of, how life works on here, here on Earth, with a, effective temperature of around 600 Kelvin, the water isn't going to exist in like some type of, Super Mario Galaxy water world. It's going to be in, a vapor or supercritical state. And that means there's no layers. It's not like a Hycean world. It's just, water in this sort of liquidy gas sort of phase.
Right. And that idea of the Hycean world, that's where you've got this water world that's then surrounded by a thick envelope of hydrogen that is keeping the water in a relatively, liquid state, even outside of what would be normally considered to be the habitable zone. So it's interesting. I didn't even know it was 100% steam, or 100% water. Like you're saying, whatever is the thickness of the atmosphere, wherever the rock begins and space begins, that it is just in that in-between point, it is just steam. From top to bottom.
Essentially, there are likely other molecules that realistically make up part of the atmosphere, but for all intents and purposes, it's at least the retrievals that I was running were finding that 100% water best explains the data, and that's sort of what we've been able to confirm by using the Hubble data. You mentioned Hycean worlds, and I do want to comment on that because something really interesting we've been finding with even the other planets that we've been observing as a part of this program is that most sub-Neptunes actually likely have a supercritical atmosphere like the one we're finding here. Most sub-Neptunes actually exist around this temperature or temperatures similar to it where water or whatever other heavier molecules that make up the atmosphere would exist in this vapor-like state. And in order for the, popular Hycean world hypothesis to exist for a planet, the planet would have to be at a much cooler temperature, say below 200 Kelvin, which in reality, most sub-Neptunes aren't. So that was another big finding from our paper and our whole sort of project that, we're kind of trying to steer the narrative away from sub-Neptunes being, Hycean worlds and more in the supercritical state.
Well, like if you took, say, Neptune or Uranus and you pushed it really close to the sun to the point that it was experiencing the same amount of flux as this planet is, would that happen to those worlds? Would they puff out? Because we call them ice giants. And they're made of various volatiles. Would it be a similar situation, do you think?
Well, at least compared to GJ9827d, not necessarily, because the compositions of these planets are very different. Another big thing we're trying to push with this paper and the other papers that are coming out of this program is that there is a lot of diversity in the sub-Neptunes that we're observing. Another one of the planets that we observed was called TOI 270d. And, the cool thing about that planet is it's actually the highest signal to noise ratio transmission spectrum of any planet in the sub-Neptune regime. And the key finding was that we found a lot of vibrational bands of methane in the atmosphere, which also happens to make it the most precisely constrained molecule in the sub-Neptune regime. That doesn't mean the atmosphere is mostly methane. It's still a good part hydrogen, helium. We're just very confident in our detection of it. But essentially the point is that a lot of the sub-Neptunes that we are observing have very different atmospheric compositions. And I can't speak exactly to what the atmospheric compositions of Uranus and Neptune are, but given how different they likely are from something like GJ9827d or TOI 270d or a bunch of the other sub-Neptunes that are out there, they would probably likely exist in different sort of states than the ones we're seeing.
Well, you mentioned this early on, though, this idea of photoevaporation having an effect on the planet. Do you see any effect of the radiation from the star impacting the planet, or is it sort of too early on the discovery cycle for that?
Yeah, no. So I don't, my expertise on this project has a lot more to do with, retrievals and sort of modeling what the atmosphere could look like. But the cool thing about working on a JWST program is that we're working with all sorts of collaborators from other institutions that do specialize in these sort of things. And it's a whole subfield of exoplanetology and just focusing specifically on how, atmospheric loss works, how common it is in planets, and how it, affects our observations. So one of the tricks for testing if, we are detecting atmospheric loss in a planet like this is we would see, I believe it's called metastable helium coming out of the atmosphere. And in our models and in our observations, we weren't seeing any of that. And, even though we are assuming that most of the atmosphere is virtually 100% water, if we were seeing atmospheric loss, we would also be detecting this helium coming out of the atmosphere. And we weren't seeing that here, meaning that, for whatever reason, the atmosphere isn't really, losing mass in this way that we traditionally associate with a lot of planets. And, atmospheric loss and all that is also still a very progressing field. And we're still developing a lot of our theories of, why it happens, why isn't it happening in some cases, and, the reasons for it.
Yeah, and I mean, finally, we've got a tool like James Webb that allows you to actually start to see maybe the clouds of material that are transiting in front of the planet, that are transiting in front of the star, and people are actually starting to be able to piece out those separate chunks of atmosphere that are being thrown away by the star, and so that definitely feels like it's the kind of mystery that will be resolved in thanks to Webb, and then maybe follow on telescopes like Ariel. So I sort of let my audience know that I was going to be interviewing you. And one of the questions from my patrons is from Scott Donnelly. He asks, are these expected to be rare since we've only found our first one?
So,
or you mentioned, I guess, a second one, right?
Yeah. So the second one I mentioned isn't, a steam world in this sense. If I'm assuming that the patron was asking for it, asking in the context of steam worlds, that's something we just can't know yet with the amount of science that's being done on exoplanets. Now, don't get me wrong, there is a lot of exoplanet science going on. Just in general, it's probably the biggest growing field in astronomy. And, there's a lot of competition for observing time with telescopes like James Webb. But the reality is that James Webb wasn't really made to do this kind of science. It's also supposed to observe galaxies and, a lot of earlier parts of the universe. And, you mentioned earlier that that future telescopes like Ariel, and I think the most exciting one is the Habitable Worlds Observatory. That's kind of what NASA and other big agencies are hoping to push the exoplanetary research into, and using the Habitable Worlds Observatory. And I think it'll require either a lot more exoplanet science over the coming years with James Webb to determine if planets like this are common, or we'll have to wait till we get more and better powerful telescopes that are more meant to do this type of science to figure out how common these types of planets really are. Because we're only really just now teasing into what sub-Neptunes on this, part of the Radius Valley look like.
Mm-hmm. Yeah, it's such a funny time. We're at whatever 5,000, almost 6,000 known confirmed exoplanets, maybe another 10,000 unconfirmed exoplanets. That there's a lot of these out there, and now we're entering the realm where we were back in, say, the late 1990s, where you just had found a couple. Now astronomers have analyzed the atmospheres of a handful of exoplanets, but that should accelerate. And so instead of us knowing one steam world, maybe we have a chat in 10 years and you'll be able to rattle off 50, right? And you'll finally get that comparison. But it's tricky, I guess, when the kinds of worlds that you're trying to study are also very rare comparatively to the other classes of exoplanets.
Mm-hmm. Yeah, definitely. And I hope to be a part of those programs that, eventually find those if they do exist. I think something that's really important to mention is when we're looking at planets that have, like including GJ9827d and TOI270d, they both have very heavy molecules making up their atmospheres. Most of the planets we've observed that are at least not gas giants have their atmospheres are mostly made up of just hydrogen and helium. And while there's not a super high amount of these molecules that make up the atmosphere, they do still make up about like half of the atmospheric mass in the case of TOI 270d. And a key aspect of doing atmospheric observations with transmission spectroscopy is that as we observe planets with heavier and more interesting molecules in the atmosphere, such as water or biosignatures, the spectral features in the transmission spectrum actually get squashed compared to lighter atmospheres, and they become technically harder to observe. Despite this, and hopefully we're able to show with this paper that James Webb is still able to detect these features. So not only are we showing that there is diversity in the sub-Neptune population, but every planet doesn't look the same, but we really are entering into a new era of exoplanetology. And, with the Habitable Worlds Observatory, I think that, and obviously that this is going to depend a lot on, how the federal budget is spent over the next, handful of years. And, James Webb had plenty of delays before it got put up into space. And hopefully, but most astronomers are still optimistic that the Habitable Worlds Observatory is going to launch within our lifetimes, and it'll be able to actually get a better idea of what not even just sub-Neptunes, but super Earths, and maybe we'll even find Earth 2.0 and seeing what the population of these planets look like.
So I got a related question from Alexander Gross. He asks, is it more difficult to probe the atmospheres of planets with heavier molecules?
Yeah, so I think that I did just kind of answer that question a little bit preemptively, but yeah, as we observe the atmospheres with heavier molecules, we require more resolving power in order to be able to distinguish all the different spectral features that make up the spectrum. With GJ9827d, with the sheer amount of water that makes up the spectrum, the features are relatively squashed a lot compared to previous planets that we've observed. And at least with James Webb, which again I have to reiterate isn't meant necessarily for exoplanetary science, is still able to distinguish these molecules in the atmosphere. So I think, even though aliens likely don't exist on this planet, it is sort of a very reassuring and reaffirming fact that we are able to distinguish this with James Webb. And, as difficult as it does get, especially when you get into super Earths and Earth-like planets, we are getting closer and closer to, figuring out what these planets look like.
Yeah, I mean, you say it wasn't meant to that, but it's one of the major, science goals of James Webb. I mean, they knew right from early on.
Yeah,
that it was going to be
compared to like some of the more exciting telescopes that are, specifically meant for planetary science.
Yeah, exactly. And so, when you think about this planet that's been discovered so far, I mean, the hope is, can we find more? Where do you think, is there anything that in analyzing this has said, okay, here's how maybe we should look for more of these things?
Yeah, so a lot of the selection that was done for, what planets we were going to observe was done before I even got on the project. So I can't necessarily speak too much to, how these planets were selected, but at least for our program specifically, we're observing 5 water world candidates. So we were looking at planets that were, within this sort of like, that were close to the radius valley and would therefore have the kind of, ambiguous atmosphere that we would like to explore more, but also B, have atmospheres that are like more prone to atmospheric characterization, because as I'm sure like with the TRAPPIST-1 system, there's a lot of stellar activity and all sorts of things that can go wrong. Even with planets, so many planets that are, they seem like, on paper, very good to observe, but, with a very active star, I think it's a M dwarf, it makes it very hard to characterize those kinds of things. So we were specifically with this program looking for less active stars, ones that planets that exist in a sort of sweet spot where there won't be too many clouds in the atmosphere, but water won't condense in the way that it'll prevent us from doing atmospheric characterization.
Yeah, I mean, it's funny. People ask me almost every day, when are we going to see the results from the TRAPPIST-1 system? We know the first two worlds are airless. Now the next ones are in the habitable zone. When are we going to find out the atmospheric composition? And I've now interviewed a couple of people here on the channel, and the answer is it's just so hard that the star is variable. And in fact, the signal that's coming from the star is making the observations of the atmosphere just brutal to try and tease out. And yet that is the best example. Like, nothing really holds a candle in terms of closeness and the way the planets line up and the one number that are the right size. Like, it's the best. And yet it's been really tricky so far. And we're going to have to wait on that. So you said that 5 candidates had been chosen. Did this one water world end up to meet that criteria, or how did the other planets turn out?
Yeah, so we're still waiting to get our data back for a couple of the other planets. This is a program that's going to keep on going for the next couple of years.
Okay.
Yeah, so GJ98270, as far as we're concerned, is a success in finding a water world. Maybe not a water world in the, what the first thing that comes to mind in, Hycean worlds or oceans, but it is, virtually 100% a water atmosphere. And, to us, we think that, we did kind of find what we were looking for. And and then with TOI-270D, there is water in the atmosphere, and, what you call a water world might be different from what I call a water world. And, that's up for debate, obviously. But with one of the other planets, we are actually finding that stellar contamination is a big problem in the spectrum, and we're kind of teasing and working through that right now. There is actually, a handful of people on this program are also working on the TRAPPIST-1 system, and I'm sure they can attest to, how much of a pain it is to, figure this out, and this big problem with small, close-in exoplanets.
Well, but I think, if you took this planet and you pushed it farther away from the sun, then that steam atmosphere would settle down and it would turn into a layer of water around the rocky core. And then it would, I think, more closely approach what people are imagining as a water world, just big.
Mm-hmm. Yeah. It's hard to, say what planets look like necessarily the farther and farther out you go, especially in this regime, because when you look at, detecting planets by transit, the closer they are to the planet, or the closer they are to the star, the easier they are to detect. So we obviously have a bias in the planets that we have detected. So, the planets that we are observing are kind of, geared towards being closer to the star, which makes them harder to characterize in a sense. But, it does give us this bit of bias that we have to keep in mind that, there are probably a good amount of smaller planets that are in the outer parts of these exoplanetary systems that we have no idea what they look like. And, they could be like that where, they are water worlds in the more, conventional way of thinking.
So, I mean, your part of this project was to work on the analysis. You were saying you're running the Poseidon software. Was that sort of is that where you live in running the Poseidon software on these, analyzing these atmospheres?
Yeah. So, my part is basically just doing all of the atmospheric retrievals for the program. There's a few other codes that we use to run atmospheric retrievals too. Some of the other collaborators do that as well, because it's good in a program like this to have different softwares all doing the same thing to, see if they reach the same conclusion. Because if there's differences in what we're finding, then, there's unexplained science that we have to figure out what's going wrong. So yeah, as we integrate over the, parameter space of, I discussed earlier, the models that Poseidon finds best fit the spectrum, then we get what are posteriors for all of our free parameters, which is basically all the ones we care about are the molecules that make up the atmosphere. And this kind of tells us basically how much of the atmosphere is made up by each molecule. So yeah.
I hope you enjoyed this interview with Eshan and Raul. Now, in addition to the interview that you watched here, Eshan and I also talked about his fascination with technosignatures and how, although technosignatures might be a more unambiguous signal, they're going to happen for a much shorter period of time when we talk about what it might take to characterize the two different flavors, biology versus technosignatures. So that longer conversation is published over on our Patreon feed that you can access for free. Just go to patreon.com/universe today, and we'll put a link in the show notes that you can access the full interview. Eshan, what are you obsessed with right now?
Me, I think the whole idea of astrobiology is something I'm really obsessed with. Whenever I tell my friends that, the few times I've told my friends, I'm actually really interested in astrobiology. My non-astronomer friends will be like, astrobiology? What does that even mean? Biology in space? We don't know of anything like that. But it's sort of this whole holistic interdisciplinary approach towards, not only characterizing, what alien life could look like, but the best ways, that we could detect it, and even if we do detect it, how to go about treating it, how to eliminate sort of all these different biases and things that we could introduce to a system. Like even for example, with like doing Mars missions, people are still looking for life on Mars. A big thing in the astrobiology realm right now is making sure that anything we detect on Mars isn't coming from our own planet and isn't our own contamination there. And I think the most fascinating part about astrobiology to me is just all the different ways you can approach it. There's, we recently launched something at the University of Wisconsin-Madison called the Wisconsin Center for Origins Research. And it's basically a collaboration between a bunch of different departments at the University of Wisconsin with this goal of, how to best characterize and, figure out the best conditions for alien life. And it includes, departments like the botany department, the atmospheric sciences department. It involves protoplanetary disk researchers, atmospheric researchers like me, and just a whole bunch of different interdisciplinary ways of thinking about how we can achieve this sort of universal goal of finding life. And I think that's very exciting to me, just all the different ways that we can approach it.
Yeah, I wonder, is that the through line when you talk to them and you're like, what got you into it? It's are we alone in the universe? Mm-hmm. And now I'm going to study atmospheres of exoplanets and hopefully chip away at that, what is possibly the most fundamental question humanity has ever asked. Mm-hmm. So it's got to be fun to be able to work on that. To normally, you wouldn't interact with these other disciplines. And yet here you are in a room talking about how you're going to find life out there in the universe, coming at it from all these different perspectives, which is what it's going to take, because no one's found any yet. So we don't know what worked.
Yeah, it's super exciting to, be able to work with James Webb data, at my age, being a grad student, being able to, work with all these different super knowledgeable professors and like seeing what real true like scientific collaboration looks like. It's, it's very like reassuring to me that this is what science is supposed to look like, and this is why it's so exciting. I think I heard a quote at this astrobiology conference I went to a few weeks ago, and it really stuck with me. I would paraphrase it a little bit, but I think it's something like, the biggest discoveries we have yet to find lie within the crossroads between different disciplines, or something akin to that. And I think that these big collaborations, these like overarching, like the Wisconsin Center for origins research, things like that, where we really are collaborating between fields that, really don't usually talk with one another. I think that's what's super exciting about science, thinking about, all the things that we might find as a result of this collaboration and working together.
That's awesome. Yeah, I love it. Well, Eshan, thank you so much for taking the time to chat with me today, and good luck with your work. Find more water worlds.
Yeah, I hope to do so. And, thank you for having me on. And I hope to be back here with more fun results to show.
Yeah, let me know when you find one.
I'll be sure to.
Now I'm going to refer you to some other interviews that we've done. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Krasaki, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I have got the message loud and clear from you that you want to know about characterizing exoplanetary atmospheres. What you want to know the answer to whether or not astronomers have found an atmosphere at the TRAPPIST-1 planets, the ones in the habitable zone. And I have tried to get the answer. This is journalism at work. And so I have interviewed a half dozen people, probably in the last year, just about the state of astronomy with exoplanetary atmospheres. And what do you know? It's a lot more complicated than we thought. So I'm going to link you to a couple of the recent interviews that I've done focusing on this very topic. And hopefully with the interview that you just watched, as well as those other interviews, you'll have this much better understanding of the tricky world that is characterizing exoplanetary atmospheres, especially around these smaller M dwarf stars. All right, we'll see you next time.